Hello everyone and welcome back. Today we'll be getting started with chapter 4 of our book reading sessions, and we'll be learning about how we can use public datasets with TensorFlow datasets. So, till date, we have trained our models using variety of data from fashion amnest to humans and horses, dogs versus cats, and all of them were available as a zip file. But we've probably realized that there is a lot of data and there are various ways to get the data with which to train a model. However, many public datasets require you to learn lots of different domain specific skills before you begin to consider your model architecture. So, the basic problem with the people today is that machine learning isn't that much difficult in itself, but that data that goes into machine training is actually of very different kinds. So it might be raw data, it might be structured, it might be unstructured data, but it is the key thing to your model architecture. A model architecture is nothing without data. So if you don't have correct data in correct format, or you don't even know the format of the data, it won't actually run and it won't actually give you the desired results. So the goal behind TensorFlow dataset is to expose datasets in a different way that's easy to consume, where all pre-processing steps of acquiring the data, getting into TensorFlow friendly API are done for you. So there it is that in TensorFlow datasets, you don't actually have to pre-process the data before using it. It's already done for you. You just have to call them and use them. And you'll see how easy it is to call the data and get the data using TensorFlow datasets in the next line of codes. So in Fashion Amnest, we used Keras to handle the data. Here you can see that data equals tf.keras.datasets.fashionamnest. So it's so easy. You don't have to zip, unzip, or read anything. You just have to call dataset from tensorflow.keras.datasets. Next, it is even easier to just divide or split the data into training and test images. So here what we're doing, we're just loading the data and in format of training and testing images and training and testing labels. TFDS builds on this idea, but greatly expands not only the number of datasets available, but diversity of data types. So if you think that TF datasets won't have a large variety of data, just have a look at the next slide. So what is here is, these are the categories of datasets that are available to us. So we can go for audios, that is speech and music data. We can go for image data, object detection data, structured data, summarization data, maybe text data, and translate and video data as well. So there is a variety of data from every genre of the society or the environment we live in, right? So there is also note that TensorFlow datasets is a separate install from TensorFlow. So be sure of installing it before trying out any samples. So what does it say is that you have to separately install TensorFlow datasets because it does not come in the Google Colab. So it might be pre-installed in Colab, but it's every time it's good option to just install it. It won't take much time and you will actually not face any run issues when you run your code. This chapter will introduce you to TFDS and how you can use it to greatly simplify the training process. We'll explore the underlying TF record structure and how it can provide commonality regardless of the type of the underlying data. So it also will be learning about ETL transformation load pattern using TFDS, right? So let's get started with TFDS. As I've already told you, first we need to install it. So just use pip install TensorFlow datasets. That's here. And once it's installed, you can use it to get access to dataset with tfds.load. Next, here is an example for fashion MNIST. So we're just loading fashion MNIST using tfds.load, and in inverted commas it's fashion MNIST that we have defined that this kind of data we want, and we are just printing the item to see if we are getting the item or not. But be sure to inspect the data type that you get in return from tfds.load command. So it's always a good idea to just print out what kind of data you are getting, because you need to make sure that your architecture data type also matches with the data type that you're getting in your data set, right? So we need to check the output from printing the items will be the different splits that are natively available in the data. In this case, it's a dictionary containing two strings, test and train. So our data set is of a dictionary type having two strings, that is train and test. These are available splits, right? So this data that we're getting from TensorFlow datasets is actually divided into two parts, that is train and test. If you want to load these splits into a dataset containing the actual data, you can simply specify the split you want in the tfds.load. So in tfds.load, you can actually split the data as you like. You don't have to use the already existing splits. So in this case, we are actually splitting for the training data. Here you can see. So this whole data that fashion is coming from, we're just getting the training data here, and we'll be printing the type of the data. So in this instance, you'll see the output is dataset adapter, which you can iterate through to inspect the data. One nice feature of this adapter is you can simply call take one to get the first record. So you just use take one and you get the first record. So in the next code, you can see we're using MNIST train dot take one. So you'll just get the first record and you just print the keys also. The output from the first print will show that the type of item in each record is a dictionary. So the data is a dictionary format. When we print keys to that, we'll see that in this image set the types are image and labels. So in this data set, the labels are actually, the types are two. One is the images and one is the labels. Or you can say the subdirectory, one is the images and one is the labels, right? So here you can see we are printing, once we print item.keys, we'll know that there are two kinds of keys here. One is the image and one is the label. So we print the first image and the first labels. The output here will be 28,28 array of values. So you can see that it is in form of tf.tensor, represented by 0 to 255 pixels, right? So output would be some like tf.tensor 2 comma shape and data type of int64, indicating that this image is class 2 in the dataset. Data about the dataset is also available using with info. So if you want to have the information about the data itself, the dataset itself, just use with info equals true. Here you can see with info equals true, and also use MNIST test comma info as well. So you can just print the info, right? So this is the whole information about the data set, that its name is fashion MNIST, its version is 3.0.0 with the description, 60,000 images and 10,000 test images. Then you have feature directory has images and labels, so that way. And here the total number of examples are 70,000. So who's the author, who actually got this all, and what's the URL we are getting it from, timestamp and all you get here. Within this, you can see details such as the split and the features within data set, as well as extra information like the citation, description, and dataset version. Now let's get started with TFDS with Keras models. So as we've already seen how to load a dataset using Keras and TFDS, Now let's see what we have to learn ahead. In chapter 2, you saw how to create a simple computer vision model using TensorFlow and Keras, but the built-in datasets from Keras using simple code like this. So what we did in chapter 2 was we were looking into computer vision, and this is how we used to get our model and dataset as well. So MNIST tf.keras.datasets.fashionMNIST that we've already seen, and we have also seen that this is the method of how we can actually load the dataset and divide it into training and testing sets, right? The Keras dataset gave an end array types that worked natively in model.fit, but with TFDS we'll need to do a little conversion work. So what we are actually doing here is that we are actually converting our TFDS model into a NumPy array as NumPy, using this as NumPy here, and we are also defining the split train and test here with batch size of -1 and as supervised equals true. Let's just understand what this code is trying to convey. In this case, we use tfds.load, passing it fashion MNIST as desired dataset. We know that it has train and test splits, so passing these in an array will return us an array of dataset adapters with the images and labels in them. Using tfds.asNumpy in call to tfds.load causes them to be returned as NumPy arrays. So, as I've already told you that tfds.asNumpy is actually used to return the images in form of NumPy arrays. Specifying batch size as -1 gives us all the data, and as supervised equals true ensures that we get tuples of input comma label returned. Once we have done that, we have pretty much the same format of data that was available in Keras dataset with one modification, that the shape in TFDS is 21, 21, 1, whereas in the Keras dataset it was 28, 21, 28. So what's the difference is actually there using Keras we were actually extracting or expanding the dimensions. But what we are actually doing with TFDS is that we are already getting it like 28, 28, 1. That is a three-dimensional data set. So we don't have to use expand dimensions and all. This means that code need to change a little to specify that input data shape is 28, 28, 1 instead of 28, 28, right? Therefore, the code becomes import TensorFlow as TF, import dataset at TFDS, and the similar. Now the code becomes tfds.asNumpy, and this we have already understood. Now what we're going to do is, since we have NumPy arrays and training images is in format of pixels, so we can divide it by 255.0 for normalization, and same we can do for the test images as well. Now we are just defining the model architecture, that we have a flattened layer with the input shape as 28, 28, 1. Then we have a dense layer, and as I've told you in the previous video that we use dropout between two dense layers only. So we have used 20% dropout here, and the last dense layer with 10 outputs. The 10 neurons, because there are 10 outputs and 10 classes actually. Right. Then model.compile with optimizer as Adam, loss as sparse categorical cross entropy, and matrix of accuracy. Finally, we just fit our model with training images and training labels. So this is how we can finally train our fashion MNIST using TFDS. Right. So there is not much to do, not much calculation or conversions to do using TFDS as we were using earlier in Keras. Now, for a more complex dataset like horses and humans, the code is kind of same and is also available. The dataset is also available in TFDS. So here's the complete code. Nothing has changed. Just that here in tfds.load we are now using horses or humans dataset. as we have already done for the fashion feminist one. Then we are shuffling the data in by 100 dot batch of in batches of 10, and this is the model. It's kind of the same, just number of convolutions layer have increased because it was much way complex data set. And you can see there is no dropout as such. And finally you can see just compile the model and just use model.history and the mod and just fit the model, right? As you can see that it's pretty straightforward. Simply call tfds.load, passing it the split that you want, and use that in the model. The data is bashed and shuffled to make the training more effective. So that's the case why we were using batch of 10 and we were shuffling the training data, right? The horses or humans data set is split into training and test sets. So if you want to do validation of your model while training, you can do so by loading a separate validation set from the TFDS. So if you want to do validation, you can just load this validation set as well. So what's it? Just split equals test. Earlier we were using split equals train, right? You'll need to batch it as well. So we are just batching it to the batch of 32. Then when training, you specify the validation data as these batches. You have to explicitly set the number of validation sets to use per epoch 2, or TensorFlow will throw an error. So if you're not sure, you just set it to 1. So validation steps, if you don't know how many you have to set for batches of 32, you just set it to 1. That's the safest thing to do, right? Next, what we are going to do is loading specific versions. So all data sets are stored in TFDS as a major minor batch numbering system. So what this is that if you want a specific version of a data set, that you can also get in TFDS. And if patch is updated, then the data returned by a call is identical, but the underlying organization may have changed, right? So it's actually a protocol kind of thing that TensorFlow uses. Then if minor is updated, the data is still unchanged, but the exception that there may be additional features in each record. Also, the for a particular slice, the data will be same, so the records weren't reordered. If major is updated, then there may be changes in the format of records and their placement, so the particular slices may return different values. So if the data is changed in the back end, there may be like 3 of these versions. So it might be changed and you might call the data and by a call and it's identical, but the underlying organization might have just changed, but the whole data that you're calling might not have changed. There might be some minor updations and the data might remain the same, but when there are major updations, then there might be change in the format of the records and the placement, so you might see some changes there. When you inspect datasets, you will see when there are different versions available. For example, this is the case for CNN Daily Mail dataset. If you don't want the default one, which at time of writing was 3.0.0, instead want the early one such as 1.0.0, you just have to simply load that. So you just have to write that CNN underscore Daily Mail, and then you have to write the version that you want for your model, right? So note that if you are using Colab, it's always good to check the version of TFDS that it uses. At time of writing, Colab was performing and it was giving TFDS was 2.0 version, and there were some bugs also. But since you will be working now, so it's better that you check that what kind of TFDS, what version of TFDS you are using actually, right? Next, let's learn about mapping functions for augmentation. So in chapter 3 only, we have learned about augmentation of data, and we have seen that there are number of functions that we can use to augment the data, and we always usually do this when we have less data on our side and basically on the training sides, right? So let's understand that you may be wondering how you might achieve the same when using TFDS, right? That way we were just writing in there was a small code, and while we were getting the directories and for validation and training sets, we were just justifying there, right? So how it is done in TFDS is that the best way of achieve this, or indeed any other form of transformation, is using mapping functions on the data adapter. So what is a mapping function? So let's just see. Earlier, with horses or humans data, we simply loaded the data from TFDS and created batches for it. So earlier what we did was we just did this data.shuffle 100 and a batch of 10, right? So this was kind of augmentation only, data augmentation, this was only. But now we can do is we can make a mapping function to do the transforms and have them mapped to the data set. You create a mapping function. This is just standard Python code. For example, suppose you create a function called augment images and have it to do some image augmentation. So this is the same kind of code that we were already using, just we have put it in the form of a function. So def augment images, image and labels that we are passing. Then we use tf.cast image comma tf.432, and we just normalize the image. We use random flip left or right on the image and then return the image and the label, right? So you can then map this to the data to create a new data set called train. So what we are doing is actually we're getting the training data. We are using this augment images function to augment that data, and then we are again constructing a new data set called the train, right? Then when you create the batches, do this from train instead of from data. So when you're creating the batches, earlier we were using the data that we were getting from TFDS. Now we have generated our own data, and this is a whole new type of data that is actually augmented one. So we are using train.shuffle here. Next, you can see in the augment images function that there is a random flip left or right of the image done using image.random underscore flip underscore left underscore right of image. So you just have to flip the images to left or right according to your needs. So using image TensorFlow add-ons, add-ons library is actually kind of like add-ons that you can install easily and then you can use them without any hassle. The TensorFlow add-ons library contains even more functions that you can use. Some of the functions in image data generator augmentation can only be found there. So it's a good idea to check it out. Using TensorFlow add-ons is pretty easy, and you can install it using pip install TensorFlow and dash add-ons. So once it's done, you can just add these add-ons in here. So import TensorFlow underscore add-ons as TFA, and when you were just writing the function code for augment images, just add on TFA dot image dot rotate, and you can rotate your image to 40 degrees. Using custom splits, up to this point, all of the data you've been using in the to build the models has been pre-split into training and test sets. But you can use your custom splits as well, right? If you want to. But what if you want to split the data yourself according to your own needs? That's one of the aspects of TFDS that's really powerful. It comes complete with a API that gives you fine granular control over how you split your data. You've already seen it already when loading the data like this. So you've already seen how we split the data. In the code you can see you can split equals train, right? But what if we want to split our own data ourselves? So it's pretty easy, that we all know the Python slice notation. So what we can do is desired slice, we can use square brackets like start and then define stop and the number of steps. So just let's see it in the code. So for example, if you want first 10,000 record of train to be your training data, you can omit start and just call for train. So train of starting from 10 till 10,000, right? So what happens here is a useful mnemonic is to read the leading colon as the first. So this would read the train the first 10,000 records, right? Data equals tf datasets dot load cats versus dot dogs, and you split the train till 10,000. So you get all the data of training images till 10,000 images. First 10,000, I would say. You can also use percentage to specify the split, like 20% split in the code. You can see split equals train of till 20%, first 20% of the data, right? Next, you can even get a little crazy and combine splits. That is, if you want your training data to be a combination of first and last 1,000 records, you could do the following. Like 10,000, starting 10,000, less 10,000 or 1,000 records. You can do like that also. Just use plus sign between and you can easily get the split. The dogs versus cat dataset does not have fixed training and test and validation splits, but with TFDS, creating your own sim is simple. So you can just split your training 80%, test 10%, and the validation 10% split. In the code, you can see that, right? Once you have them, you can use them as you would any named split. One caveat is that because the datasets that are returned can't be interrogated for length, it's often difficult to check that if you have split the original correct set correctly or not. So as you know that datasets are returned and their length cannot be interrogated. What's the length of the dataset? So you can actually not check that whether you have done the split correctly or not. To see how many records you have in a split, you have to iterate through the whole set and count them one by one. So here's a code how you can just do that. Train underscore length I for I in enumerate data train data, and you can just get the training data length. This is a slow process, but it is only used for debugging purposes only. Now, let's just get started with the code. It's not a very big lines of and large lines of code as you already seen. We'll be just using a quick use of TensorFlow datasets, and you'll see how easily you can just train a simple fashion MNIST model. Right, so let's get started. First, just install TensorFlow.datasets, and while it's running, let's just go ahead and see what next we're gonna do. Next, we are gonna just import TensorFlow as TF, and we are gonna get TensorFlow datasets as TFDS. And as you can see, our line 1 of the code is already running and it's installing datasets. So all the requirements are already satisfied. Next, what we are going to do is we are going to get the training and training testing images as well as labels using TensorFlow DS as NumPy because we want it in form of NumPy array, and TensorFlow DS.load a fashion MNIST, like a single line of code we can use to just get our data and nothing else has to be done. So you can also define the split, train and test, right? So it's done here, and while it's loading the data, it's getting the data and extracting it. I can show you that the next step would be to just normalize the images, right? The training and the test images by dividing it simply by 255.0. Then the model architecture that we always do, we have a flattened layer, a dense layer, then a dropout layer with 20% dropout, and then finally a dense layer with 10 neurons because we have 10 labels of 10 labels or 10 classes, right? While it's running, actually, let's just see that we'll be using Adam optimizer for compiling and loss with the sparse categorical cross entropy and metrics of accuracy. And now it's run. So I've already run this before. You can see the previous accuracy and the loss, and just use model.fit with training images and training labels with epochs equals 5, and it will run very quickly. It won't even need any GPU or TPU because the data set is small. It's not very big data set, so it will run very quickly. And then we'll just evaluate the model on the test images with test labels, so how it's doing. And finally we'll just use test images to predict it as well. So you can see the training accuracy is about 87%, which is kind of decent in this data set, right? So once it's done training, we'll just evaluate and we'll get the prediction for our test images, and we'll write the classification as well. So what kind of classification it gives on the test image for like the first the zeroth test images, right? So as you can see, let me run it first for you. Yeah, you can see it gives me the test label 4. So we can say that the image at 0th position of test images set is actually of the label 4 or class 4. It might be a shoe, it might be a sneaker, it might be a heel, but we can see from here that the fourth one has minimum loss. So it has the largest value because the probability is 10 to the power minus 1, while the rest of them have 10 to the power minus 6, minus 5, minus 2, minus 10 even. So they are all very smaller, while 8.834677 and 10 to the power minus 1 is way more large than the 10 to the power minus 10 or 10 to the power minus 6 or 5, right? So that's it for this. This is whole fashion MNIST dataset, and you can see it's just so small code, and you can just run it so easily using TensorFlow datasets, and there is no hustle that you have to pre-process the data or you have to split the data, you have to do something. It's all just done for you, and you can just simply write it in a single line and use it for your model, right? So I hope you have learned a lot about TensorFlow datasets, and next we'll be understanding about TensorFlow records. And I hope you like these videos and just stay ahead with us. And this is chapter 4, and I'll be putting this whole code in our GitHub only. The link would be in the description. Do check it out, and if you have any problem, do share it in the comments, or you might reach out to our Twitter handle, or maybe reach out to me in person. So thank you so much and keep learning.